yesterday, I think you got an introduction to general relativity for the people who were not, maybe too familiar with it yet. And I have to build on that because my job this morning is to show you, if you have general relativity, how do you get, first approximation to what gravitational waves look like for a binary system. So in other words, if I have to put it into formulas, there we go. It's my job this morning to start from here, the Einstein field equations, and get to the gravitational waves if you have some inspiral, right? Because that is the base thing that we try to measure in our detectors. Now, we can go into an enormous amount of detail there, but we will see that you already get to a large part by doing part of it in a Newtonian fashion. And we will discuss that in more detail as we go. But just out of interest, the Einstein field equation was something that you had discussed a few days back, yes? It's going to be very important because we're going to refer to it every now and then. And for the people who need a reminder, so I might be redoing some of the stuff that you had already seen a few days back. The Einstein field equation is this guy over here. And that equation tells you how space-time is curved. That will be the left-hand side of the equation, given a certain amount of mass and energy and motion within space-time. Right? That's what the TMU stands for, the thing that carries how much energy and mass is there, but also how much the mass and the energy is moving. It's a tensor equation, although we're not going to do too much with the tensorial aspects of it. That means that you have the freedom to go to any coordinate system that you want. That is really the hallmark of general relativity. You can build up general relativity from the idea that you should be able to do your physics from any coordinate system that you want. Right? You already know this obviously from special relativity, where you get to do your physics in different coordinate systems called inertial systems, right? The Lorentz transforms brings you from one system to the other. But if you want to extend that to a situation where you can go to any coordinate system that you want, and then you build that out, then ultimately you end up with the Einstein field equations. But it also gives you this tensorial behavior, because tensors are the objects, conceptually speaking, that tell you how things will change if you go from one coordinate system to another, no matter what other coordinate system you try to go to. And that is really why things turn out in tensors. There's a number here. That number, if you plug in the G's and the C's, you will be familiar with the fact that in general relativity we tend to write the Newtonian constant G, small number, as 1. We also tend to write the speed of light as 1. And so in my calculation I will do that as well. I will have my G's and C's equal to 1, but at key moments I will plug them back in, so you get a feel for what the number should be if you plug things back in, yes? This is one of those moments. If you have G equal to 1 and you have C to the 4, then this is a pi, which is an okay number, right? It's not too small. And it might give you the impression that, the right-hand side of the equation is, sizable. But in real life it isn't. If you plug your G's and your C's back in, G is 10 minus 11 in SI units, and C is 10 to the 8th. And so to the 4th, it's a bigger number, divided by is a very small number. Then this combination turns out to be ridiculously small. Right? In SI units it's about 10 minus 45 or so. That's another way of saying that the right-hand side of the Einstein field equation is ridiculously close to 0 in everyday situations. Also telling you that if this is 0, then the left-hand side, which gives you a curvature of space-time, tends to be, non-curved at all. And by non-curved, I mean special relativity, Minkowski space-time. So the smallness of this combination here tells you that if you want to have any curvature at all, that means gravity, you have to put in an enormous amount of energy and momentum to compensate for the smallness of that number over there, right? This is why you need so much mass and energy to make curved space-time. So I'm going to leave that back out, and again I will put the G's and the C's back in at key moments. But the idea then of general relativity conceptually at the end of the day is not very difficult. What you have to do, you have to take a piece of space-time. You're interested in what happens over there, how space-time is curved. That means plug in how much mass, energy, how much things are floating about. So this is typically the guide that is given. And then you have to solve the equation for the other side, which gives you the curvature of space-time. And the curvature of space-time is the thing that tells you what gravity is. Now, with that gravity curvature, then you can calculate other stuff. So principle, in a sort of a series of steps, this is a very easy equation, but in practice it's very difficult. Because, well, multiple things. For one thing, this is not one equation. These are 10 equations. So that's one thing. It's all buried in the fact that these are tensors, and depending on which mu nu value you take, it's really a set of 10. And at the same time, this is highly nonlinear. The left-hand side, you're trying to solve for the metric tensor. At the end of the day, that's the measure of the curvature of space-time. But the metric tensor appears in that left-hand side in a highly nonlinear way. So not only does one have a very big set of equations, it's also a nonlinear set of equations. And the crappy thing about nonlinear differential equation systems is there is no general way of solving them. So pretty much that means every time you want to solve this equation, you have to go back to a drawing board. There's no foolproof way to always get the solution. That makes it very difficult, unfortunately. And well, to put a little perspective to this, this equation that Einstein wrote down in 1915, 1916 was solved for the first time only a few months after its publication. That is the famous Schwarzschild solution, the non-rotating black hole solution. That only took a few months, but then the next valid full solution was in 1963 or so, the Kerr solution, the rotating black hole. So it takes a couple of decades to find an analytical solution to this equation. This is complicated. But here's the good thing. Under a certain set of approximations, you can make the equations much more simple, and then you can solve this. Now, I understand that Anurad already spoke to you about this in some detail, so I will redo some of those steps, not to upscale her, but really to have all the calculations at the ready again, because we're going to need them in the rest of the story too. Here's one of the approximations that we will make. We're going to do the following. We're going to look for a special solution. We're going to assume that space-time is flat. And by flat, I mean it's just special relativity. Now, that assumption tends to be highly justified because, again, for the reason we were just discussing, this is a very small number. So that means this is very small. And if this is 0, then the solution would be Minkowski space-time. Minkowski space-time, we like to write this object, right? Minkowski metric tensor. Now, if you don't read tensors too well, that's not the point. It is the conceptual part. This is just the part that says this is the non-curved space-time that you study in special relativity. Okay, all good. Now, but we're interested in the following. Suppose you have a Minkowski space-time now, and you put a perturbation on it. You try to make it slightly non-Minkowskian. Then the solution to the left-hand side of the equation should be the Minkowski space-time plus a little extra. The little extra we're going to denote as this guy over here. That's a little extra. How much space-time is not exactly Minkowskian anymore. And that's the thing that's going to be our gravitational wave in a moment. Now we are going to assume, that's one of the assumptions that we're going to make, that the perturbation to Minkowski space-time, the not perfect flatness of space-time is very small. And at the end we will see that tends to be a highly justified assumption. Well, that has immediate consequences. One of them being that if you're going to plug that guy into that guy and work all of it out, you're allowed to throw out every term that has an h squared in it. So these things are ridiculously small. I mean, this is small, but this is smaller still. There's a slightly added conclusion to what we've written here, and that is not only do you get to throw out the square, so to say, the curvature on the curvature, but also that it doesn't change too much. So that if you take the derivative of the curvature, right, the small perturbation, that too is small. So we're going to throw out all combinations of h itself, but also h maybe multiplied with its own derivative. By the way, there's some physics here. The fact that h is small does not necessarily mean that its derivative is small, right? You can easily write down a function that itself has a small value but ramps up very quickly. But if you would do that, then that means that that function, sure, it might be small over here, but if it has a high derivative, it will be very big over there. But what we would like is have a solution that has small throughout the whole space-time that you're looking at. So you want the derivative to be small too, because otherwise you have smallness here, but not so much smallness over there. So when I say this, I really mean I don't want it to be small somewhere, I want it to be small everywhere, and that gets me to the derivative also being forced to be small. Yes. Now, this is the moment where we now have to do our work. We have to plug this guy into the left-hand side Janssen field equation and then see what we end up with. But because of these approximations, the nonlinearity that I was talking about, the problem, so to say, of solving this equation, goes away, because everything that is h squared, the nonlinear parts, you're literally throwing out. And then you end up with a linear set of equations, and the nice thing about linear sets of equations is that there are general methods of solving them. So I wasn't there. Did Anodadas do this exercise? Did she go through it, or did you do this in the afternoon session? Ish. Sort of I see a wobbly hand. I see another wobbly hand. Wobbly hand means we did it, but not in too much detail. Okay, then this is one of those steps that I will redo in some detail. Not in full, because nobody wants to see a full board of algebra. You will get the written out solution that I have, but I want to focus a little bit on the conceptual part, yes? So, the idea is as follows. The left-hand side Janssen field equation, again, has nonlinearities in it. But the highest derivatives that you will get on the left-hand side are second derivatives. Right? You will get the metric tensor, curvature of space-time, will appear in second derivatives. Does anyone know why, by the way? Why not first derivatives? Or zero derivatives? I mean, why doesn't the thing itself appear? Well, it appears there, but it gets multiplied with another thing that contains itself. It sounds like a mathematical question, but at the end of the day, it's a physical question. It's a question of physics. Why does the left-hand side, if you want to look for curvature of space-time, why are we looking for second derivatives of the metric tensor and not first derivative or third derivatives for that matter?
Acts like a force.
That's actually, I'm going to take that. I was slightly going to go in a different way, but I like that comment so much that I'm going to go for it. Let's take a small step outside, yes? And then we'll go back to this derivation. So the fact that this is second derivatives in this metric tensor, the reason that I'm harping so much on this is because this is second derivatives, and if you linearize it, you will get an equation with second derivatives. Namely the wave equation that at the end of the day is going to give you waves. You cannot get waves with first derivatives, right? So I'm harping so much on this, that this is second derivatives, because I need my second derivatives to get my waves. But then I asked, well, why second derivatives? And you said, because otherwise it would not be a force. Was that the...
Well, I think it acts like a force.
Yeah, I like that comment so much that I very easily go off on a tangent. This is one of them, but it's an important one. Yes, one of the things that you can do with the metric tensor, the thing that tells you of space-time, how much it is curved, the curvature of space-time tells how you should move, right? If I try to move in a straight line, but the space on which I'm walking is itself curved, that means I don't walk in a straight line anymore. So you can imagine that if you were to write down what would be Newton's first law, straight line constant velocity, in a curved space-time, you will not end up with a straight line and constant velocity anymore. You'll end up with something that feels like a force, like something is pulling on you. There isn't, that's the curvature of space-time. You're not going in a straight line because space-time is curving your path, not a force. But you feel it as if it's a force. Now that equation, by the way, thank you very much, is really key parts that I think is going to help us. This will be Newton's first law in flat space-time, yes? It simply says my position x is a function of my own time, proper time, is second derivative is 0. That means straight line, constant velocity. Okay, good. This is in a flat space-time, this space-time, special relativity. But if I'm going to go to a non-flat space-time and I try to walk in a straight line on something that is curved, then this side is not 0 anymore. Instead it becomes, well, and really it's not about the details for people who are seeing this equation maybe for the first time, but it's about the concept. Becomes this horrible expression over there. The point is that it's not 0. Right? This equation is called the geodesic equation. What's the key part here? That this, first of all, is not 0. That will be the force that you feel, gravity. And it's a function of this big gamma, and gamma is itself a function of the first derivative of your metric tensor. So the forcey part is really true. The first derivative of the metric tensor is what you feel as a force. The first derivative metric tensor gives you this guy over there, making the right hand side not zero, telling you that you're not going into a straight line constant velocity anymore. Yes? But let's go to Newtonian physics for a moment. If somebody's pulling me on that direction, what I can do is accelerate myself into that direction and sort of compensate that guy's force, right? I can go to a coordinate system such that somebody's trying to pull on this side with a rope or something like that. I literally compensate that by accelerating to that frame that goes in that direction. So if I feel a force, somebody is pushing and pulling, I can mitigate that force, make it zero, simply by going into an accelerated coordinate system. I can compensate somebody's force. Now, in the field, this is what you would call a fictitious force. So apparently what you can do with first derivatives, the thing that you are actually feeling, this guy, you can compensate simply by going to another coordinate system and completely cancel that guy out. So what does it tell you? The fact that I can compensate my forces by going into different coordinate systems, I can cancel this and make it zero again, means that this is not a real measure of how much curvature I have. I can cancel my curvature. I can pretend as if there's no curvature at all, because I can make it zero by going to this other coordinate system by first derivatives. So all of that is a long story to say that a first derivative of the metric tensor, this guy, cannot be a true measure of gravity, cannot be a measure of how much space-time is pushing me in one direction or the other, because it can always compensate it. And remember, one of the hallmarks of general relativity is that you have the freedom to go to any coordinate system. So that means there apparently exist coordinate systems in which all my forces are gone. There's no curvature anymore. Well, that means there was never curvature to begin with. So I cannot do curvature calculations with first derivatives. I need second derivatives at the least. That's the story here. So all of that is me saying that following Einstein's reasoning, this part of the equation, if you want real curvature, not the part you can compensate, real curvature, you need second derivatives. That's why this guy is an equation in second derivatives. And that's why if you're going to plug this in, back to the off of my tangent now, back to the real story, that if I'm going to plug this guy in, I am going to get an equation for my unknown h, right? The curvature that I have on my Minkowski spacetime, y is going to be a second order differential equation. This is the part, plugging that in and working all of that out, that takes forever. I do it with the students, they take 30 minutes or so. It's not that hard, but it does take a while. I'm simply going to write down the answer. The answer is this. Well, let's do the simple case first. Let's first go to the case where there is no energy around. So I still have a space-time that is special relativity, flat. There is a small amount of curvature on it, that's the thing that I'm looking for. But I'm going to pretend that that curvature is trying to be there even though there's no energy or matter. It simply means I have flat space-time with a small amount of curvature, but no stuff trying to interfere with that curvature. That's me making this zero just for a moment. This guy into that guy ultimately gives you that. Note the linearization. Yes? The h that I'm looking for only appears to the first power. That's the step that I made by doing this approximation over here. Notation-wise, people are familiar with the symbol that I have here? If not, I'm happy to write it out, because it is important. That symbol is the Lagrangian operator. It tells you how many space derivatives and how many time derivatives in what combination. That combination here is this. Well, let's do the one dimension just for simplicity's sake. 2 space derivatives minus 2 time derivatives. That's if you write this out. Yes. Now I should be more careful with people more in the know if you write this out in Cartesian coordinates. Otherwise it would be more complicated. But there we are. So, plugging that guy into there for a moment, assuming that there's no stuff around disturbing h too much, you're going to end up with this equation. You might as well forget about the minus 1/2 because of the 0 over there. And this is, well, what in any other field of physics you would call the wave equation. It tells you that whatever h is, the non-flatness, the small non-flatness of otherwise flat space-time. Anyway, what is the answer to this equation? It's an undergraduate question, this, right? It's about optics and classical mechanics and. What's that, sorry?
A wave equation.
Yes. Wave equation, in principle, that means sines and cosines will be a solution, but only sines and cosines in a very particular combination of my time and space. It's a partial differential equation, and partial differential equations don't tell you what the thing looks like. It only tells you how it's space-time, how it depends on its variables. The solution to this equation is t minus x. Actually, plus would work too. Again, this is for the special case of only one spatial dimension. This is the solution. It works. You just plug it in, work it out, and you see that it neatly gives you 0. But it tells you more. And you're free to add any amplitude that you want. It tells you a little bit more too, because this combination, that's the point that I was making about the partialness of this differential equation, that it gives you a relationship between how the things spatial position, how the things moment in time are related to each other. And this combination tells you, well, you can actually see it happen here. Let's make this the minus option. Plus would work too. Let's make it a minus for a moment. It tells you that if you go up by 1 second to get the same answer out, x should also have gone up with 1 second. Right? That's the only way to make the internal argument stay the same. Now what does it tell you? That means if you wait 1 second, whatever the thing is has moved exactly 1 unit in x direction. 1 unit in space per 1 unit of time. In our units, where c is 1, that would be the speed of light. So this wave equation enforces, by mathematics alone, that whatever the solution is, it will travel with the speed of light, with the speed 1 in my units. And the plus minus simply means it could travel that direction and that direction. The equation doesn't care. But this is not the only solution, I should add, because a cosine will be a solution too. But it's a linear equation, right? That was because we linearized it. And the nice thing about linear equations is that if you have 2 solutions and you add them, that solution, that outcome is also a solution. So I can add as many sines and cosines of this shape with each other as I want and still end up with a solution. And the cool thing about adding sines and cosines is, by this Fourier analysis, you can make other functions out of it. So, if you want, this is a solution too. It looks like it didn't do anything. I said h, the thing that I'm looking for, is equal to h. No, I did add something. The h that I was looking for was a function of time, moment, and position. But what I say over here, it's, well, time and position, but only in this particular shape. Now, if you don't buy the Fourier argument, so to say, just add sines and cosines, you can plug this guy directly into here, and you will also see that it works. Now, this too is an important conclusion, because what this means is that this wave equation that we got from the Einstein field equations tells you that a perturbation on otherwise flat space-time will first of all travel with the speed of light, that's one, and secondly, that it will not change shape. The only thing that came out of the equation is how it moves through space, not what its shape is. And that's very good news. Because that means if you have a flat space-time here, Jessica, I used you a few days ago to make a gravitational, you're typing, but a few days ago she was standing over there, so suppose that she made a gravitational wave. Suppose that Jessica makes a gravitational wave, again. Yes? She makes a gravitational wave, and suppose that between us, space-time is as special relativity as possible, and the wave is also small, then that wave will travel towards me, again, with the speed of light, but without changing shape. So that means whatever I'm going to get is whatever it was when it was sent out. That's a good thing if you want to measure stuff happening from far away. That's what is enforced now by this equation. So that's pretty cool. For the aficionados, to go from here to here, there's an enormous amount of detail that I left out. and I'm just going to mention it, and this is one of those things I've written out for you, and we will upload it on the page. Namely, that if you plug this guy into here, you don't actually end up with this equation. You end up with an equation that's much more complicated. I'm not writing it out. I mean, if you want to see it, I'll be happy to. But you're going to end up with a much more complicated equation. And that means that the more complicated equation does not give you this solution. So it looks like a fudge here. I threw this guy out. Well, here's again the magic of general relativity, the freedom that you have to go to any coordinate system. Well, remember that we were just talking that you can make some of the forces disappear by just going to a different coordinate system? I'm using the same trick. This complicated stuff is going to give you, well, part of your gravitational wave, but I'm going to go deliberately to a slightly different coordinate system than I started out with. I'm going to go to a slightly different coordinate system such that in that new coordinate system this part is exactly 0. That's the freedom of general relativity. You can go to different coordinate systems. Your equations will slightly change, and if you're very clever about this, then you can make them change such that the stuff in your equations that you don't want vanish. That's what we call gauging. And of course gauging means slightly different things in different fields. In general relativity means pick your coordinate system just right so your equations become more simple. In this case it means go to a coordinate system where this guy is gone. Now again, the details I've written out for you and you will get from me, but to put it into conceptual terms, there's Jessica again making a gravitational wave sending towards me. If I happen to find myself in the coordinate system before I did this little trick, then this is not the equation, this is not the solution. I'm going to get a much more horrible conclusion. The gravitation will not be a nice sine or a cosine, for instance, but something that's much more complicated due to this part. But I'm standing over here and I don't like the way that her gravitational wave looks, and I say, you know what, I'm just going to go to another coordinate system. And another coordinate system simply means I'm not standing where I'm standing, I'm just going to make myself move a little. I'm now in a slightly different coordinate system than I was before. And I'm going to move myself in such a way, my slightly different coordinate system such, that the stuff that I don't like about her gravitational wave gets cancelled out. That's what I'm doing. That's the freedom of general relativity. Go to a different coordinate system. That was me doing this right now. Slightly different coordinate system. Some of this stuff cancels out. So that's good. That gauging part will be on paper for you. You might be tempted to think, aha, but what if I don't want to have a gravitational wave at all? I'm going to move slightly different still to completely cancel Jessica's gravitational wave. So that in my now yet again new coordinate system, I don't feel a gravitational wave at all. In other words, I'm going to make this guy disappear too. Well, that's a nice exercise in algebra. That cannot be done. You cannot find a coordinate system where this guy is gone. And this relates back to the discussion we were having before, that a true measure of curvature is second derivatives. There's no coordinate transformation you can find where second derivatives gets cancelled. First derivatives gets cancelled, second do not. So this part, if you want, is a real gravitational wave. No matter what coordinate system you try to go to, this guy will never be cancelled. But you can cancel this. Once you've done that, you're here, then you have that solution. Now that very special coordinate system is called the Lorentz gauge. We should add here, it's named after Lorentz force and Lorentz transform, same guy. Nobel Prize 1902. He actually did not come up with this thing. Just a trick of gauging, he used an electromagnetism, where you can get your potential fields to be slightly different and make your equation simpler. It's the same trick, used on a different situation. So, well, that's what you get if you're a Nobel Prize winning physicist. All of a sudden things get named after you even though you didn't do them. Alright. So far so good? Because next step, this was in vacuum. I made it 0 for a moment. Again, going to Jessica and me, I pretended there was nothing in between us. In fact, I even said there was no Jessica. There was nothing that made the gravitational wave. Oh, that's by the way another thing that tells you. The fact that I get the solution that I cannot gauge away, that I cannot make disappear, means that gravitational waves apparently can travel through vacuum. They don't need a medium. Okay. Now for our story, I'll end here at the end. I have to add a source. I cannot throw this guy out. It turns out that you can play the exact same exercise here. Just reinstate the 8 pi and then whatever. Well, this is Jessica. Team UU. And her typing, because motion is also in there. You can do the exact same exercise, including this gauging part, going to the right coordinate system, and you will end up with, well, almost the same equation. There's a small nuance that I will point out. It's the same equation that we got here, equals 0. But now it doesn't equal 0 anymore because you have a source. You might remember I had the -1/2 here that I could cancel because with 0 anyway. I don't get to cancel anymore because I have the 8 pi over here. The small nuance is that what you're solving for is not the gravitational wave h itself, but a slightly mathematically altered version of it. That's simply for mathematically pragmatic reasons. This h bar, not to be confused with h bar, is defined as the original gravitational wave, the one that I'm actually looking for, this one, minus 1/2 of the flat space-time times what is called the trace of the gravitational wave. This is a small nuance. It doesn't change the procedure that you have to do to solve this equation. The reason that this is introduced, you might recognize that this part looks eerily similar to that part. Right? That's deliberate. If you're going to take this equation, it would be much more simple, mathematically speaking, if this part, well, would not be there. Now remember, a second ago I was saying you can make terms in physics or your mathematics disappear by going to the right coordinate system, this gauging. That's what we did here. But this guy you can make disappear simply by a redefinition of the h that you're solving for. It's nothing to do with going to different coordinate systems. It's just a mathematical redefinition of the thing. If you would happen to define h bar in this way, then this part is exactly going to cancel that part, and the equation that you have to work yourself through is much more easy. So it's for pragmatic reasons that this is introduced, but the idea is still the same. Again, Jessica? Sorry, Jessica. Hope you're okay. If you shout when it's not, okay? There's more people in this room that I know by name, so at some point I might actually pick somebody else.
I just thought if you pick someone who actually has to listen, that would have a better effect. You make me permanently.
Oh, okay, I'm distracting you. I'm sorry. So suppose that Toby is here. Okay, so I'm sorry, I'm going to take you now. Okay, right, this is you now. And I want to know what the gravitational waves look like that are sent from him towards me. Then I take the energy momentum of Toby and the way that he's moving. Solve this equation. Once I have found my h bar, again for simply redefinition of what I meant by h, I can calculate the original h that I was looking for. That's my gravitational wave. Okay. So here's the wave equation, but now with a source in it. This part is still the second derivatives will still give you something that moves with the speed of light. So that part is still retained. But clearly, the solution will now depend on what t looks like. So we have to solve this equation. Now, it would not be a good idea to, for every single situation, for the Tobys, and take them, and then for every single situation plug it in, and then try to solve this equation, complicated. It would be nice if we had a general solution to this equation that always works, no matter what t would have looked like. And that equation, or that solution exists, outside of general relativity. Right? This equation is known in many areas of physics, including electromagnetism, optics, etc. For people who want to look it up, it's called the sourced Laplace equation. And people long since have already solved it. In fact, I wrote it down already. Here it is. So, stepping outside of general relativity for a moment, just writing down the mathematics of this equation. This operator on some unknown function equals some source, given per situation, happens to have this as its solution. You can get there by Green's function methods if you're interested. Right? The only thing you have to do is you have to take your source, divide it by this particular combination, then integrate, and there's a 4 pi having to do with the Dirac delta function, blah blah blah, then you get the solution. So instead of starting here and plugging in T mu nu first, no, take this guy, then plug in your T mu nu, and then perform the integral if you're so interested. And then you have the solution. Now, if you don't believe in it, this is a solution, fun exercise to give to students, not you, bachelor students. Plug this guy into there, take a big pot of coffee, work your way through it, and you will get to the solution. Now, I will, so it's mathematically completely valid. But I will say a few things about what it means. Because you can actually very easily read this equation, and now it comes in handy that I know some people by name. Because, what does this equation tell us? Well, we already saw that without anything, it tells you that something is moving with the speed of light. Okay? Now, if this whole room is a source of gravitational waves, and they're all sending it towards me, then what I have to do is I have to take each and every individual one of you and how much you are individually sending me your gravitational wave and add everything together. That's what this integral does. That's what this integration variable does. X prime. There's two x's. One x is where I am in a given coordinate system. Right? Let's make the corner of the room here the 0 of my coordinate system. In that coordinate system, my location is location x. Well, here's somebody who I know by name. So Louise is standing over there. She's making a gravitational wave. Well, not yet. Can you? Okay. Well, yeah, there we go. make sure you're a quadrupole. Okay, then we're good. Okay. Now she's making a gravitational wave. She is at location x prime with respect to that coordinate system. The distance between her and me is x minus x prime. That's this point over here. So if I want to know how much I'm getting gravitational waves from her, I need to know how much she, at her location, x prime, is doing some moving. And, well, then I just have to integrate over every single one of you and how much you are doing your moving, and then add everything together. Right? So I guess that makes sense. That's what the integral tells you. By the way, I'm not putting that in. That's what the mathematics tells you that comes out. I mean, it just happens to be so that the physics is very easy to interpret. But there's more going on. First of all, this comes from the mathematics. Her gravitational wave will go down. This number is how much how many meters she and I are apart from each other. So whatever she sends out will diminish 1 over as the wave is traveling towards me. Now, each and every one of you is in a slightly different position, so your amount of smallerness will be different. But there we are. So that's what that tells you. And the important part here too is what called the TR. It's called the retarded time. Retarded is not a statement about, it's not a mental state, it says something about it's a delayed time. Okay? It's defined as my time, where I am, what I'm measuring now on my clock, minus the distance between me and the person sending me a gravitational wave. Again, this is the mathematics tells me that should be there. Because look, if I'm over here, and I'm catching Guido, I'm going to take you now. Yeah. Okay, so I'm standing over here and I'm getting his gravitational wave, then what I'm measuring right now, his gravitational wave right now, is of course the way that it was sent out a few seconds ago. Well, how many seconds? Well, this amount of seconds, right? You have to divide by c. So this part here compensates for the fact that what I'm seeing now is what he was doing a few seconds ago, and it took a while for that wave to hit me. That's why it's called retarded time, delayed time. So at the end of the day, what does this formula tell you? It simply tells me every single one of you sends out a gravitational wave. All of your gravitational waves diminish over distance. And what I'm seeing from you now is how you sent it out a few seconds ago, depending on how far away you were. And then I add everything together. That's a solution. So this is the sourced Laplace equation. And look what we have over here. A source Laplace equation. Sure, I mean, it's a tensor, and I promise to leave the tensor part out a little bit. It's a tensor, but the mathematical structure of the equation is exactly the same. So, borrowing from there, I can immediately write out what my gravitational wave will look like. This goes to the other side, gives me 16 minus 16 pi, but this guy is going to cancel 1 over minus 1 over 4 pi. I'm going to get that's my solution, the general solution to this equation. And in principle, we're now done, right? Well, you know, this is the end of the lecture, so to say. I'm going to do more, but on the practical matter, we have everything that we want. This room makes gravitational waves. Depending on how you're moving and doing your thing, I know this. There you go. Depending on how you're moving, I know the T mu nu of this room. Plug it in here. If I know your T mu nu, I know it in full detail. I can do the calculation, get the gravitational wave that comes out of it. Well, this is the one that I'm looking for, but I can solve it from here. I get my gravitational wave, and at the moment, so that determines the shape, so to say, of this gravitational wave. Remember over here that I said that at this point it could have whatever shape. This guy just tells you that it moves with the speed of light when it's in vacuum. Now, if you guys, you're not a vacuum, but if there's a vacuum in between us and you've made your gravitational wave, then this equation will tell me the shape of that gravitational wave. At some point, that wave has detached itself from all of you guys. In the intermittent vacuum towards me, this equation takes over, and that tells me that whatever your guy's shape was, that's the one that I'm going to get so many seconds later. And in that vacuum part, it will not change because that's what this guy told you. So, we can now calculate gravitational waves, at least in a situation where space-time is hardly curved, right? All of this is only the assumption that it's just special relativity plus a little extra. Okay. All right, well, all the cards on the table. Let's apply to the binary system. Because that was my promise, that we're going to get a gravitational wave coming from two black holes orbiting. You might be getting uncomfortable now. Because wait a minute, black holes, and I thought we'd talk about an otherwise very flat space-time. Yes, so I'm sort of breaking my promise now. How can I have this guy as the thing on which I have a gravitational wave if I'm talking about two colliding black holes, for instance? That's true. This is why this calculation is not fully correct. Fortunately, the black hole thing, black holes only feel that they're black holes when they get very close to each other. If you're far away enough from any object of mass, it will look very flat like Minkowski spacetime. That's just me saying, if you're far away from mass, things look as if there's no gravity anymore. So what I'm going to do here is going to be true at least when the two stars, when they're orbiting, are not so close to each other that this guy should really be replaced by something black holey. Okay, but under that approximation, that's what we call the inspiral phase 2 days back when I spoke about this. That's a good approximation. If you do want to do this in the case of a black hole, then you're in a lot of trouble. Because then this guy has to be black hole space-time. That means all of this doesn't work anymore. And well, you have a lot of work to do there. Tanja Hinder this afternoon will speak a little bit more about these sorts of calculations. They're very complicated. Okay, well, let's start applying this. I'm going to erase this. How am I on time, by the way? That the clock doesn't work.
10 to 10.
10 to 10, okay. Thank you. Insert obligatory joke about relative time, etc. Okay, so let's immediately start applying it now. We're going to, first I'm going to make this expression slightly more simple. I'm going to make some more approximations. So far I've only made one. Gravitational waves are small. Okay. Let's do the following. let's again, well actually, let's not draw it out, I'll actually just use this example again. So I'm going to take Renz's gravitational wave, Guido, Toby's, etc. Every one of you do that integral over there. But the distance between me and Guido is not so much different from me and Renz. It becomes very much different. Sorry, I'm just going to stand over here. Okay. Okay. So this is pretty much what there's a difference now. Yes. Okay. So that means the x minus x prime in that equation is clearly not the same for us two as for me and Louisa again. I needed somebody far, far away. Okay. But if I'm going to stand 5 kilometers out and you're still here, only a few meters apart from each other, then the difference between me and Rens and Louise, to take that example again, on those 5 kilometers is really not that much anymore. So if I'm going to make myself the receiver of the gravitational wave very far away from the source, which happens to be the case for binary systems, then this number is going to be ridiculously close to a constant. Well, that constant I'm simply going to call r. The distance from me and this whole room, no matter how much distribution of you within the room is. Well, that's going to clean up the equation, yes? So, all of a sudden, equation is simplified by quite a lot right now. I could do a little bit better still. I think what you work through with Anuradha is, remember that I was saying you can use the freedom to go to different coordinate systems to, originally was to remove a term in my complicated equation. You can also pick a coordinate system in such a way that my gravitational wave only operates in spatial dimensions, right? The gravitational wave will stretch space and time. That's what the Greek letters stand for. Which combination of space and time are you looking at? But you can deliberately pick a coordinate system in which the gravitational wave will only operate in spatial dimensions and will leave time unaffected. It's called the TT gauge. That too is a nice exercise to work through, that can always be done. That one I've also written out for you, but I'm going to assume that coordinate transformation has been made. We go to coordinate system not only where that complicated equation became more simple, but also one where the best that the gravitational wave can do is stretch space and not time. Now space, we tend to write with not Greek but Latin indices. It tells you it's only the spatial part. Here's what I'm going to do. I can write this equation where I'm now in that system where there's only spatial part in such a way that this integral becomes much more simple. Now what I will do, I will write down the outcome, and depending on what you want, we can go through the calculation. I will say how it's done, but if you want to actually see it deliberately done, we can go through it. But I will write it out first. You can do it in such a way that this, let me write it out first. That this is the outcome, where I is going to replace a whole bunch of stuff within this integral. This is the definition. I is defined as the location of all of you, right? These were your coordinates of each individual one of you, times your mass density. How much kilogram per cubic meter do each and every one of you take up? That's what we call mu. And I still have to integrate. That integral is that integral. Prime, prime, prime. Any idea how it got there? It's nothing to do with physics at all. This is just a mathematical step. I'm not testing you, I just want to see if I'm making too huge of a leap here. Before I saw wobbly hands, but now I don't see wobbly hands, so I don't think I can make this step in one go. So let me go through it in some detail, yes? It has to do with the energy momentum tensor. energy and momentum in physics, including in relativity, are conserved. That means that if you take the derivative of the energy momentum, you should get 0. It's a little bit more than that. Energy, conservation of energy doesn't just mean that you cannot make energy disappear from here to the next second. There's also continuity to it. That if energy gets lost over here, then it should have traveled through space. Right? That's the continuity equation. The same thing with currents and charges and probabilities in quantum mechanics. So you cannot have something disappear here and end up someplace over there. It must have traveled in the intermittent space. If you were to write that out, little side note here, then the conservation of energy and momentum will look as follows. Will be this. Simply says that the derivative, go back to Greek indices just for a second. There you go. This is an equation that tells you more than just that energy momentum cannot get lost from one second to the next. It also tells you that it should move through space. If this is not clear to you, it might be because of the Einstein summation convention. There's a lower mu and an upper mu, and that means you have to add all the possibilities from mu and add everything together. So this is just shorthand for the following equation, that if you take a time derivative of this guy, you should add to it the spatial derivatives and this combination is 0. This is literally just that equation but written out. This is what I was talking about. This is if this guy changed in time, then this must have moved through space. That's what it says. Yes? Now there's still one index to go, this nu over here. And nu is either itself a component of space and time, 0. Then this T00, that part of the energy momentum tensor, is how much mass there is per cubic meter. In other words, that's your mu over here. So the mu over here is just the T00 that I have over there. Now if I make this guy 0, then that guy is 0. And what that means is that I can replace that guy. Yes?
Maybe it's silly, but didn't we just move to a coordinate system where we only go over spatial coordinates? So how is we still have the zeroth?
No, that's true. That's a good point.
Or is that the coordinate transformation?
This operation I do now, you can do before the coordinate transformation.
Okay.
It will not affect the outcome, but it's a good point. I'm sort of mixing up the order because I went to a space where the zero part, where the temporal part was not there, but now I'm doing something in the temporal part. Let's pretend I did not do this step yet. Okay. The point that I'm making here is that you can turn this guy. Well, if you would have this guy's derivative, spatial derivative, you can turn it into a temporal derivative of the amount of mass. That's what the conservation of energy and momentum tell you here. So the only thing you have to do, if I want to go from here to there, I have to make it so that this part gets two derivatives in front of it. Spatial derivatives. Because each of those spatial derivatives, using this trick, I can replace by a temporal derivative of the amount of kilograms per cubic meter. So how can I do that? Mathematical step. Partial integration. I can literally, by partial integration, replace this guy by two of its own derivatives. Use those two derivatives using this rule, and then it turns into the T00, which is the cubic meters, the amount of kilograms per cubic meter. So from here to here, that big step that I was making is just a combination of energy momentum conservation and partial integration. So again, I can work out the details, but I hope conceptually you understand that this is what happened there. And now then I will go to the one where I go to the special case, the coordinate system. Oh, I should not have erased that. I'll write it back. I will go to the ij part, which is defined as xi, x this is partial integration, you can replace a multiplication with an x by a derivative with an x on the integral sign. That's what partial integration does. That's what I did here. This, by the way, has its own name. It's called the second mass moment. But the important thing, going back to the physics of this, is that we have now made a simplification again. Because what we now have, this final equation that I have now tells you that if I want to see a gravitational wave to begin with, remember all of this is gravitational wave, I need masses to accelerate. I need two time derivatives. You cannot make a gravitational wave by linear velocities. In fact, that's going back to our discussion from the beginning. That's again the fact that you need accelerations to, or second derivatives to see something in general relativity. The curvature of space-time is a second derivative thing, and that's reflected nicely here too. So you need you need an acceleration. That's what this tells you. An acceleration of mass here. Okay. All right. Well, let's apply now to the case of two objects orbiting each other. That's this here. Let's make our life simple. Let's take an XY frame. Let's put two masses in there that by complete Newtonian dynamics grabbed hold of each other and are orbiting each other. Now for simplicity's sake, I would make the two stars masses have exactly the same mass. This is to not have too much algebra to write out. If you don't like that, go back to your classical mechanics. It tells you two-body system, two masses can also be replaced by a reduced mass and a total mass system. So this can be adapted to a non-equal mass, but for simplicity's sake, I will make it an equal mass situation. Since they have the same mass, that means they have a center of mass in the middle. That also means that if I just apply Newtonian dynamics to say how they're moving around each other, I know what the x of one of these masses looks like. Let's say that the distance to the center of mass is some value of r. High school trigonometry. Not mistaken, it should be this. Where omega is the orbital, the angular frequency. Reminds me to get a sip of coffee because I couldn't think of words anymore. This is one of the two masses. The other one has very much the same thing. The y-coordinate, that's again for one of the two masses. Question, what is the mass density of one of these objects? Because I'm going to need it here. A certain amount of kilograms per cubic meter. I know the kilograms, that's n. But it has to be per volume, right? That's what you mean when you say density. Well, if you want to have my mass density, you have to put a box around me and measure its volume, take my mass and then do the division, etc. But I should not make the box too big because then I'm going to take you into it in account as well, yes? So in real life, I want to have a box that only encapsulates me. So I need to have a sort of a tight-skinned box, so to say. Now in Newtonian mechanics, these, sure, they're extended maybe in volume, but gravity-wise, they're point particles. So I need a box that is exactly 1 point size, exactly a one location object. So if only we had a function in physics that tells you where exactly one object is and it's not someplace else. Yeah, function, distribution. It's the Dirac delta function. Yes. So if you multiply this guy by a Dirac delta function, then you have what you're looking for. Now, you might think, well, how is this a mass density? Well, it's because the Dirac delta function, its unit, its dimension, this is one of the defining properties of the Dirac delta function, yes? This is a volume. The outcome is unitless. That means the Dirac delta is 1 over volume. Which volume? Well, exactly the volume that encapsulates the one thing you're looking at. So this guy is exactly per cubic meter. And the exact amount of cubic meters that contains that one particle. Then still multiplied with m, because you need a mass per volume. That's what you're looking for. Okay, but then we're done, because the only thing I have to do is plug these into here and perform the integrals. And then I should have the answer. Well, then I still have to get that guy and take 2 time derivatives, but then I'm there. And then we're done. Now here's another nice property for Dirac delta function. They are very easy to integrate. Right? You always say the derivatives kill integrals, right? They cancel each other. No, the Dirac delta functions kill integrals. So if you're going to plug that guy into there, then let's do it here. You are going to get, well, again, the Dirac delta is exactly cancelled by the integral. So I'm going to get this remaining m. And then, well, it depends on which of the components of this object I need. There's a few of them, right? I mean, we have, since x, y are the only parts where the thingies are orbiting, I just need the x-x combination, x-y, and the y-y combination. And all that grouped together makes a nice little matrix, tensor, that contains all of these components. Now, each and every single one you can calculate. If you want the x-x component, well, that means these two x's are these two. If you want the y-y component, then the y-y, then you're going to plug in 2 of these. If you want the xy, then you're going to take their combination. I will write down the answer in a moment. This is just plugging in. But you can already see one thing immediately. You're always going to have some cosine times cosine, or a sine times a sine, or a sine times a cosine combination. Yes. Now, you know from your trigonometry that a square of a sine and a cosine can always be written as a non-square of 2 times the frequency. This is the double angle formula of trigonometry. Now, if you apply that, let me write down the answer. It tells you something extremely interesting. Again, let me write the answer first, because I don't want to struggle on stage. I'm just going to get it from my notes. Give me a second. All right, there we are. If that's okay with you, I will immediately write down this guy. So I'm going to plug the 2 over r in front, and I've already taken the 2 derivatives of that, time derivatives. So I'm actually going to write down the remaining gravitational wave in the bar notation. Again, it's 2r over I dot ij. That I over there with all of this plugged in is going to give you 8 omega squared over r mr squared. And here's the double angle formula that I promised I would use. That the squares of the sines and cosines make a double frequency term. Oh, plus a constant, but because I'm going to take 2 derivatives, the constants are going to drop out again. So I will end up with only this. That's my gravitational wave. This guy tells me how much the x direction is stretching. This guy tells me how much my y direction is stretching, and this is their combination, the xy combination. These two, what you call the plus polarization, only in either in x or in y. You can see they're half a phase out, because the sine and cosine are half a phase out. That's good for gravitational wave detection. It means only one arm gets stretched, and then the other one, half a period later. And this is what we call the cross polarization. But the important part is the factor 2 that comes in here, because it tells you that whatever the source is doing over there, its orbital frequency appears as twice the frequency that you measure over here. And that's the general rule in general relativity, that the highest contribution of a gravitational wave, its frequency is twice that of the source. In this case, a very simple case, because the source itself is a sine and a cosine. But since again we are in linearized theory, That means I could have had a source that was written by Fourier series in sines and cosines of both the frequencies, and each and every single one of them will play by this rule and have double their frequencies. So this way you get gravitational modes. In this particular case, there's only one mode, and it's twice the frequency. So gravitational waves make space-time wobble with two times as fast as the source is. And in this combination. So there you go. We have our gravitational wave. Okay, good. Oh, small comment. There are two of these, and I only use one. I secretly use two. Remember, the integral is over every single one of the sources, but I have two of them now, two masses. So that means whatever I plugged in, the other one has a similar contribution, and with the squaring, etc., they give exactly the same contribution. So I've smuggled in a factor of 2 to account for both of these masses doing the moving. So what I have here is not just the gravitational wave due to one particular mass doing its acceleration around the center of mass, but the combined effect. That's what you have here. Good, that's a gravitational wave. Alright, now in my remaining time, let's talk a little bit about, well, if this system sends out gravitational waves, that means the system cannot maintain itself. It's losing energy. It's carried by the gravitational wave. Well, if it loses energy, that means the system will have some dynamics to it, and it's not too difficult to derive that. So in our remaining time, let's derive that. But first, let's talk for a little bit about why gravitational waves carry energy to begin with. Right? I mean, we all know this, gravitational waves have energy. Well, we know that stuff that moves through space-time have energy, but why would it be that space-time itself, its own movement, is also a source of energy? And again, I thank you again for our starting discussion about first derivatives. Let me give you a quick argument why a gravitational wave carries energy. There's many arguments, but this is one of them. Remember that equation when we're having the discussion about you need second derivatives of the metric tensor to measure curvature, and I wrote down this perturbation from Newton's first law, that if you would have no curvature, then this would be 0. Things would move in a straight line, constant velocity. Now, if that's not the case, here's that equation that I wrote down before. And again, the details do not matter. The point is not 0. This was the discussion we were having before. That this guy, it's called the Christoffel symbol, contains first derivative of the metric tensor. Yes? It's the first derivativeness that's important for my argument now. If you would see this as Newtonian physics times m, then this will be the force, mass times acceleration. That means all of this will be a force. Earlier I called it the fictitious force. It's the force that you feel because space-time is curved. But this guy consists of first derivatives of the metric tensor. Yes? Okay, if you squint through the mathematics, but just remember from your classical mechanics, what I'm saying here is that a force is directly related to the first derivative of a thingy. Now if you go back to your classical mechanics, the derivative of a thingy is a force. What is that thingy? What is this physical interpretation of it? What's that, sir? Velocity? Sorry, I should say its spatial derivative of a thingy is equal to its force. Something like this. Force is equal, it's Newtonian physics here. It's minus the spatial derivative of some scalar thingy. Scalar thingy being therefore the potential energy. Now the fact that general relativity tells you that if you have a curved space-time and the first derivatives lead up to a force, the thing of which you take the first derivative must carry the information of an energy. And this is not just by comparison, this is really what is the case. The metric tensor, the cursor of space-time, is itself a source of energy. That's what you see here. Now in our case, the same is true for the gravitational wave. In fact, that is what makes your interferometers squeeze and stretch. it's the force due to this gravitational wave coming by. So h, gravitational wave, is itself a source of energy. And that also makes, right, but what I want to do now is I want to show you that if you have leakage of this energy, because we've seen that gravitational waves are carried out, they go with the speed of light, that means we've now seen they take energy away, then as it comes from here, that's going to make the dynamics different, that's going to give you your inspiral. But in order for me to calculate that, what I need to do is I need to have an expression for the energy of a gravitational wave. Well, it's not just that h that I wrote over there. That's a little bit too simple. You have to do a little bit more to it. Right? It's a little bit of more work to it. That work is not entirely trivial for the following reason. Here's the Einstein field equation again that I think Anurada introduced yesterday. And I said at the beginning that the left-hand side is curvature of space, and the right-hand side is energy, the stuff that makes the curvature. Okay, fine. But I'm also saying that the curvature itself, the metric tensor, is itself a source of energy. So I'm sort of saying the left-hand side is curvature, the right-hand side is energy, as if they're completely unambiguously split from each other. But at the same time, the stuff that you put on the left-hand side is itself a source of energy. That's what we were just discussing. So exactly how does one make the split? How much of the curvature is actual energy, and how much should appear on each side of the equation? There's ambiguity there. It's mostly semantics. It's slightly dependent on author and context, how much of the curvature you would take into account for the total energy, and how much is the energy that you made while sending your gravitational wave. So in general relativity literature, you have many definitions of what you mean by the energy, depending on how much of the curvature you take into account and how much you do not. There's ambiguity there. But in our case, we have linearized our theory. We made the left-hand side only consist of single h's, no squares of h's. Yes? I do. So all of that left-hand side has only one h. That was deliberate. And that resolves, in our case, the ambiguity. The fact that we've split up our single h's as being the curvature means that whatever is not a single h, but for instance squares of h's, therefore can be ferried over to the other side and be seen as the energy of the gravitational wave. Yes? So again, there's ambiguity of how much of the energy you put on the left-hand side as curvature and how much you put on the right-hand side as energy momentum tensor. But since we are in the situation where we have, by premise, called the curvature only the single h part, every non-single h part can be ferried over to the other side and be seen as the energy of the gravitational wave. You will end up with an extra addition to your energy momentum, right? You were making gravitational waves, plus extra. And that extra part, therefore, must consist of second combinations of h with itself. It's that guy that I'm interested in. That's the energy of the gravitational wave that's being sent out from the system. That calculation I will not show in detail, but again I will give you just the answer of it. And with that we can finalize and by calculating the final dynamics of the orbit system. If you want those details, those have also written out, so you can read up on the exact details, but I will give you the answer. You will find that this expression, starting with this is my gravitational wave, this expression over here becomes this second mass moment that I have over here multiplied with itself. The multiplication is what gave me the h squared part. Right? That was the part that we ferried over to constitute the energy of the gravitational wave. For simplicity we're also going to average, because the energy is not the same at every moment. You can average this out. You don't have to, but for our case that's simple enough. You have a perfect circular system. The averaging is very simple. You get a very nice expression. Almost there. The gravitational wave was two derivatives. But what I'm really interested in is how much energy is leaking away from my system. So I need to take yet another derivative to not just get the energy, but how much energy is flowing through space away from my system. If you go through that calculation, you're going to end up with 3 derivatives. 2 because they came from here, and 1 extra because of the leaking. And this formula, if you want, you could call this the luminosity of the gravitational waves. That's why I call it L. It's how much energy is leaking away because there's a gravitational wave represented by this object. It's a famous formula. It's called the quadrupole formula. So when I was asking Louise to make a gravitational wave, I was saying, well, just make it just right, because I want you to make it such that this is not zero. Not every motion will do it. You have to have a very particular type of acceleration. Okay, good. For completeness, I will write down what you will get if you plug in R H and RI into here. I have to steal this from my notes. I don't want to get the number wrong. Yeah, there we go. Again, this is just the algebra of plugging that I into here and then doing the averaging procedure. You are going to get 128 over 5 times m squared times r to the 4. That comes from here, right? You have to square this thing, m squared r to the 4. And because you're taking yet another derivative, you're going to get yet another omega in front, and that gets squared. So you're going to get an omega to the 6. So what do we have now? If you have a nice little system, 2 stars orbiting each other, and you know their orbital periods, so you know how fast they're moving around each other, omega, and you know what the masses are, then this number tells you how much energy that system is leaking away due to energy being sent by gravitational waves. I promise I will plug in C's and G's at the right moment, so here's one of them. Put back the G's and the C's. Get C to the 5, big number, divided by a very small number. Gives you a ridiculously big number. Gravitational waves carry an enormous amount of energy. Oh, you still have to multiply it with solar masses in kilograms, yes? This is really big. Gravitational waves carry an enormous amount of energy. That should not be surprising going all the way back to our Einstein field equations. Over there I mentioned you need an enormous amount to make space-time curved. We made space-time curved, that's our gravitational wave. Well, that energy that you had to put in is stored someplace. Well, this comes back here. So the number that you had to plug in here, the bigness of that number represents itself as the bigness of that number. And that's sort of counterintuitive because you think gravitational waves are very small, so they probably don't carry a lot of energy. No, they carry enormous amounts of energy. That's what you see here. Okay, well, let's go to the final few minutes if you indulge me, because to get to the final part, we now have how much energy the system is sending out. And I'm interested in how does that make the system change. Remember, we were doing this exercise by Newtonian dynamics. That's good enough, because we were in Minkowski space-time, flat enough, so you don't have to think about Schwarzschild and black hole solutions. It's simple enough that you can do Newtonian mechanics if you don't get close enough. So the only thing I have to do now is write down the following. I have to write down the energy, Newtonian energy of this complete system. Take its time derivative, because I'm interested in how much the energy of this system changes, and set the change of this guy's energy equal to what gravitational waves are sending out. Yes? Now before I write down the formulas, just conceptually speaking, the Newtonian energy of this guy I can write out, and maybe you can already squint ahead and see that the energy is dependent on the period, how fast they're moving around each other. Yes? So this expression, the energy of this system, will contain the period of the 2 stars around each other. I have to take its time derivative, so I'm going to get an expression for the change of the period of that system. That I'm going to set equal to this, or minus this. That's the energy, and it comes out. Does anyone remember what I wrote here? Because I accidentally wiped it out. It's a testing question. 128 over 5 m squared r to the 4 omega to the 6 plus g's and c's. Okay. The period is also here. That's the frequency of the two differential of the two stars around each other. So this guy is a function of the period and only of the period of the system. The energy of the Newtonian system I can also write as a period, and because I took its time derivative, you're going to get this guy is going to be something that contains the time derivative of the period. This side contains the period to some power. That gives you a differential equation for the period as a function of time. And that you can solve. That gives you how much the period is changing as a function of time due to the send out of gravitational waves. For completeness, I will write out the formula itself. First of all, it takes too long. I'm just going to make it slightly easier. The energy of the Newtonian system, and this is just Newtonian mechanics, is ultimately given by this. This is the kinetic energies of the two stars and their mutual potential energy, with everything written back into their period. Solve that. Classical mechanics exercise. This is the expression. The other side is already here, but an omega is going to be 1 over the period to the 6 with some numerical factor. Put this into here, and the remaining differential equation that you're going to get is this one. The change of period of the system is proportional to the period itself to some crappy power. Crappy power comes from this. That crappy power. By the way, do people recognize the 2/3? Classical mechanics? Periods and 2s and 3s? Stars orbiting each other, they obey particular rules.
Yeah, third law.
It's Kepler's third law. That the period squared is equal to the distance between the stars cubed. That's what I did to rewrite this into this. That's going to give me the thirds, so to say. It comes from Kepler's third law. A is a constant, and for completeness I will write it out. But clearly that's not where the physics lies. It's a crappy constant. It's all of that stuff. It's 96 over 5 pi 4 to the power minus 1/3 2 pi m to the power 5/3. The thirds are again from Kepler's third law. Now that's a nice differential equation. Can be solved. Does anyone dare to venture a guess? It's a nonlinear differential equation, but it's not too hard. You can do this by hand. I did it by Mathematica. I just asked Mathematica. The answer is this. There's again some number in front, not too important for our story. 2 to the power 9 over 8, 3 to the power 3 over 9, blah blah blah. A is a t minus t0, and all of that to the power 3/8. That's how much the period of the orbital system is changing due to the send out of gravitational waves. That's a function that goes down in time by some non-trivial amount. The t0 is your integration constant. Oh, excuse me, this should be t0 minus t. That's the integration constant for you to fix. If you plot this out, it will look like this. Period as a function of time, very quickly goes at point t0. The period will have gone to 0. It takes 0 seconds for them to orbit each other. That's the moment of collision, so to say. Yes. So you, as a human user, for all differential equations, an integration constant, you have to plug in by your physics. T0 is the moment of coalescence when the two stars hit each other. with that, you can see that for the longest time the two stars don't notice too much about the send out of energy unless they get very close to each other. If you wait long enough, and all of a sudden they rapidly go into each other. But that also means that the frequency of the gravitational wave will ramp up at that moment. The ramping up will appear at many places. One of them is, of course, that they will orbit faster. The omega has gone up. But remember, the omega also appeared in the amplitude. So as the two stars get close to each other, they go faster, faster, faster. They ridiculously ramp up all of a sudden. The frequency goes up when you get close to T0. But the amplitude goes up even more because it goes with the square. Now if you remember from 2 days ago when I showed you the general plot of the inspiral phase, there was a sort of a sinusoidal thingy. That's this. But when it got very close to each other, all of a sudden they start to move ridiculously much more fast than a few seconds before. That's this part. This ramping. And then all of a sudden you have this one burst of energy at the very end, the biggest burst. That burst is that guy going up. And that's how we call it chirp. That's the thing that you try to measure in a gravitational wave detector. How am I on time?
2 minutes over.
2 minutes over? Okay, well, no obligatory moment on time is relative, etc. I will say one finalizing comment. Again, all the details, mathematical details, I try to stick to the conceptual parts, but the details I have written out for you if you really want to look through them and recalculate everything. But I will finish by saying, well, where does this stop being the correct description? And we already spoke about it a little. First of all, we made the assumption all the way in the beginning that the gravitational wave h are very small compared to an otherwise flat space-time. Now that usually is justified because, again, Einstein field equation, you typically only have a very small amount of curvature because this number is so small. Okay, so that is typically justified. But another assumption that I made was that the mechanics of this orbital system is Newtonian, which is okay because stars, when they see each other from somewhat of a distance, they look pretty much Newtonian. But it does mean that if they get very close to each other, so that will be this part over here, this approximation really doesn't work that well anymore. And you have to work harder. So what people do, and I think Tanya this afternoon will speak about this much more, is that they use an approximation scheme that they say, well, this is only the first order approximation, Newtonian, and then they add terms to it to correct for the fact that there was really not Minkowski space-time to begin with. Yes, there's many more effects that you have to build in, but this is one of them. So that means you have to add terms to it. Now there's people in the audience who probably know much more about this, but I understand that the status is there, 7 terms in? Stefano, you know this? Something-ish, yes?
It depends on which part, but yeah, certainly.
So think about this. They started this approximation scheme where they added corrections for the fact that it's not really Newtonian. It's called literally post-Newtonian corrections. In 1983 or something, I think they started. So we're almost 40-ish years later, and well, they got 7 terms now. Right? It's a complicated equation to solve. But that is the one. The complicated one is the one how you correct for all the things that we are now approximating, and that's the one part of it that is now used in the data searches when you actually compare what comes into the detector with the theoretical approximation. So all of this is correct up until here-ish or so. Yes? And then, well, you have to go back to the drawing board. Anyway, that's it from my side. Thank you very much.